Welcome to today's lecture on supply voltage scaling. In the last two lectures, we have discussed how static voltage scaling is done and a voltage level, a lower voltage level is assigned to the entire circuit, and we have discussed various techniques, approaches used for this purpose. Today, we shall focus on multi-level voltage scaling, and here is the agenda of today's lecture. As I mentioned, multi-level voltage scaling is an extension of static voltage scaling, where two or few fixed voltage domains are used in different parts of a circuit. That means, earlier what we did, if you have got a circuit, entire circuit is having a particular voltage VDD and that is being scaled, that is your static voltage scaling using single voltage. Now, we are considering a situation where inside a single chip, maybe SOC or maybe a single circuit, and different parts of the circuit can be assigned different voltages. We can create different voltage domains like this, and maybe this circuit will operate at say 1.2 volt, this can operate at 1.0 volt, this can operate at 0.9 volt, like that. That means, within a single circuit you have got different voltage domains. And how these domains are created we shall see, and this is called multi-level voltage scaling. And here we are using two or few voltages, not many, maybe 2 or 3 or 4 different voltages are used. And now, what is the basic concept? As we know, high VDD gates have less delay, but higher dynamic and static power, and low VDD gates have larger delay, but lesser power dissipation. It is already known to us. Why? As you know, the delay is proportional to 1 by VDD and 1 minus VDD VT by VDD square. So, as voltage increases, delay decreases, and as voltage is reduced, delay increases. And then, as you know, power, particularly the dynamic power or switching power, is proportional to alpha CL VDD square and F. So, as the voltage increases, the dynamic power dissipation increases. Not only dynamic power, but static power as well. As you know, static power dissipation is proportional to VDD into I leakage, and both voltage, I mean the leakage current can also be dependent on voltage, and as a consequence the power dissipation increases as voltage increases, and delay of course reduces in this case as the voltage is increased. So, we can say that if we use high VDD, say VDD high, then delay is less, VDD high, delay is less and power is more. On the other hand, if you use say lower voltage, say VDD low, so lower supply voltage, then delay is more, but power is less. So, we can use 2 or more voltage levels, and we can judiciously combine them such that there is overall reduction in the power dissipation. However, we shall try to maintain the same performance level as it is the main goal or main challenge of supply voltage scaling techniques. So, this is the basic concept, and we can create voltage islands at different levels of granularity, such as macro level and standard cell level. So, we shall be having different voltage domains, and that can be done at different levels. For example, the different levels of granularity. It can be macro level, that means it can be a big circuit block like ALU, AD2 converter, transmitter, receiver, like that, or it can be at the standard cell level. So, we shall discuss both of these techniques, and then as I mentioned, total power dissipation can be reduced without degrading the overall circuit performance. That is the overall goal. So, with this objective in mind, we shall proceed to discuss multi-level voltage scaling. First, let us focus on macro based voltage island methodology. Here, it targets towards an entire macro or functional block to be assigned at different voltages at the time of high level synthesis, and starting with an intermediate representation known as directed acyclic graph DAG. High level synthesis involves two steps, scheduling and allocation. So, what you are doing here, we shall be performing multi-level voltage scaling at macro level, and as you know, it is done at high level synthesis stage, high level synthesis. As you know, synthesis of digital circuits involve a number of steps. One of them is the high level synthesis, it is followed by logic synthesis, then it is followed by layout synthesis. So, in high level synthesis there are two basic steps. Number one is scheduling, and second step is allocation. So, what is done in scheduling? Different operations are schedules at different time steps. For example, suppose you have to perform this operation, say you have to realize this function operation, say A into B plus C into D plus you are doing addition here. So, E into F. So, suppose you have to realize this function, that means A into B plus C into D plus E into F. So, the corresponding DAG will be, say A B multiplication directed acyclic graph, and then you will be performing another multiplication here, multiplication where you will do multiply C and D, and they will be added together with the help of an adder, and then you will require another multiplier. So, to perform multiplication of E and F, and then you will be performing addition, and here you will get your function f. Now, what you can do in time step 1, you can schedule this multiplication 1 where you are doing multiplication of A and B, and then you will also do the multiplication C and D and multiplication of E and F. So, all the three are scheduled in step 1 in time step 1, and in time step 2 we will do this addition, and this will be followed by another time step where we will do the third addition, I mean second addition. So, this is how you can do. So, here you can see in this case we have the option of scheduling this multiplication E and F either to the first time step, or you can schedule it to second time step, still it will perform the purpose. That means, this is the job of the scheduling. You may have the choice of scheduling some functions at different the different time steps. So, this is what is done in scheduling. Then in allocation, you are essentially allocating different circuit elements, circuit blocks to different functions. So, multiplier has to be allocated to the operation multiplication, adder has to be allocated to addition. Suppose this particular is scheduled, multiplication is scheduled in this step. In this case, what you can do, multiplier 1 can be allocated to this operation, multiplier 2 can be allocated to this operation. Then since these two multipliers are performing in time step 1, this particular operation, if it is scheduled to second time step, then you can allocate multiplier 1 to perform this multiplication as well. However, if it is scheduled in step 1, then you cannot do it. So, you have to use another multiplier. So, a third multiplier is required, has to be allocated to this operation. So, this has that means that scheduling and allocation are interdependent, one affects the other. Scheduling may increase the requirement of hardware, that is the reason why these two are interrelated and it has to be done. Now, in this particular case, what we are trying to do, we are starting with a DAG. This is the directed acyclic graph as I have told, and then the slack of the off critical path can be utilized for allocation of macro level modules of low VDD to off critical path operations. So, look at this particular directed acyclic graph. So, we find that this multiplication, this multiplication, this addition, that means 1, 2 and this addition 1 and 1, these all 4 are on the critical path. So, but however, here what has been done, this multiplier 1 is performing this multiplication operation, then multiplication 2 is being performed by another multiplier, second multiplier, and addition is being performed by a single adder in this time step and in this time step. So, which are all these are all on the critical path. So, you cannot really change their positions. However, you have a multiplier, another multiplier 3, which can start computation in time step and has to finish before the end of second time step. So, it has a slack. So, what you can do, it can overlap the multiplication operation over 2 time steps because of the slack availability of slack in this off critical path. So, this multiplier can be assigned a lower supply voltage, and obviously delay will increase, it will take longer time, but as long as it does not exceed the 2 times time required in 2 time steps, then there is no harm. That means, as long as the computation is complete before the third time step starts, you can proceed with this particular allocation. So, this is the basic idea of this multiple VDD circuit. Let us take up another example. This is realizing differential equation. So, to solve differential equation, this is a little complicated, as you can see. It involves a large number of multipliers and adders. You can see 1, 2, 3, then 4, 5, 6, 6. There are 6 multiplications, then 6, 6. Then there are 9, and 9 is also a multiplier. So, you find a large number of multiplication and a large number of additions are there, and also a comparator is required, this operation 11. So, 11 different operations are there. Now, in this particular case, you can see this is a critical path 1, 4, 9 and 10, 2, 4, 9 and 10 are on the critical path. However, this 3 and 6, operation 3 and operation 5 are not on the critical path. So, we have the option of allocating some low voltage and utilize the slack to achieve lower power dissipation. Essentially, what we are doing here, we are trading slack for lower power, and in this case, as you can see, these timings are given here, that means shows that it is requiring the various timings which are shown here, that means multiplication is requiring 18 time cycles, that is why 18 clock cycles, that is why it is starting at time instant 19, and here it is starting at time instant 37, and so even again another 18 clock cycles are required to complete this multiplication. So, this operation can start at the 44th clock cycle. So, this one has some slack, this multiplication can start at timestamp, I mean clock cycle 1, and here there is a slack. You can see even if it starts at time clock cycle 19 8, still it can perform the operation. Similarly, it can start at 19 or 26. So, there is a slack. So, these two multiplications have slacks in the range 1 to 8 and 19 to 26. This slack can be utilized to assign lower supply voltage to these multipliers. Similarly, this multiplier and this addition has larger slack, as you can see, because only requirement is that before 44th clock cycle you have to complete these two operations. Same is true for these two, I mean addition and comparison. So, you can assign multipliers of lower supply voltage. What does it really mean? That means in your library you must have macros which will operate at two different voltage levels. That means, they are optimized for different voltage levels to offer operation in two voltage levels. One can operate at VDD-H high voltage level, and another can operate at lower voltage level VDD-L. It is not necessary that they will have only two voltage levels, you can have more than two voltage levels as well. For example, in this particular case we have the choice of 4 different voltage levels 1.8, 1.5, 1.2 and 0.8, 4 different voltage levels. As you can see, the multipliers and adders which are on the critical path, they have been given the voltage 1.8. That means, these modules will operate at 1.5, 1.8. On the other hand, this multiplier is operating at 1.5 volt. This multiplier is operating at lower voltage 1.2 volt. Still, it is maintaining the time required by this. Similarly, this multiplier is operating at voltage 1.2. This adder is this multiplier. I think this is adder. This adder is operating at 0.8 volt. Even then, it will satisfy the timing requirement. Similarly, this adder is operating at 0.8 volt, and this comparator will operate at 0.8 volt. So, in this way, you can see at the time in the allocation step, we can allocate different types of multipliers, adders, comparators to different operations. So, and this is also known as technology binding. So, technology binding means by what type of circuits you are realizing a particular operation. And as you do this, there will be a significant reduction in power dissipation, as it is shown in this particular table. So, here you can see a large number of DSP circuits have been compared, biquad, DCT, differential equation, FFT, FIR filter, lattice and so on. So, you can see the number of they require different types of functional elements to realize the circuits, and originally if all are allocated the voltage 1.8 volt, the power consumption and area requirements are given in these two tables. So, power consumption is given in this table, area requirement is given in this table. On the other hand, if you use multiple voltages, as I have told 1.5, 1.2, then this 1.5, 1.8, 1.5, 1.2 and 0.8, you can have significant reduction in power dissipation. You can see there is a power reduction of about 40%, 39.59%. So, there is a significant reduction in power dissipation. And of course, whenever you are using just reducing the voltage, you are not changing anything else, there will be no increase in area. So, area will remain same, and the only reduction will be in the supply voltage, and that will lead to reduction in power dissipation, and you can see you can reduce 39.57%. Of course, this part we shall discuss later, where we can use different threshold voltages that are used for reducing leakage current, that we shall consider later. This is based on a paper published in the year 2008 in International Journal of Systemics, Cybernetics and Informatics. So, we can see this is the module level voltage scaling, where you are assigning different voltages to different modules and achieving lower power. Now, coming to standard cell level, as you know, you can have gates on the critical path, and also there can be gates on the non critical path. As you can see in this diagram, here this is a critical path shown by the red line, and the critical path delay is 10 nanosecond. On the other hand, this blue line, the green line is showing the non critical path. These two gates are these gates are on non critical path. So, what you can do, these gates can be assigned lower voltages, lower voltage VDD low. On the other hand, gates on the critical path can be assigned high VDD, VDD high, and this is, and as long as the that this critical path delay 10 nanosecond is exceeded by assigning low voltage to these gate, to these 3 gates, it will serve the purpose, that means the performance will not be degraded. However, you will be getting reduction in power dissipation. So, this is the basic idea of standard cell level voltage scaling. Now, this is shown how different gates are clustered. Normally, you know, the gates which are assigned high voltage levels are clustered in one place. Similarly, gates on the low voltage levels are clustered in one place, because you have to apply power to them. So, unless they are placed in one, they are clustered in one place at the time of placement, then routing will be difficult, and providing power them will be difficult. That is the reason they are clustered together. So, for example, in this case, these flip flops, these gates without any SED, these are on the critical path. So, there they can be assigned higher voltages. On the other hand, this flip flop, this NAND gate, this flip flop, this NAND gate, this NOR gate, this NAND gate, they are on the non critical path. So, this is, you can form a cluster of low level voltage VDD-L, and this is here you can form a cluster of VDD-H. So, in this way you can have 2 different types of clusters, and you can assign them low and high level voltages. One point you must have noticed here, there is a mention about level converter. So, later on we shall discuss about it, the need for level converter. Whenever you require when the signal passes from one voltage level domain to another voltage domain, there is a need for level converters. Later on we shall discuss in detail about the need of these level converter. So, if for example, in this table the number of level converter requirements have been given here. I did not discuss about it, but later on the need for level converter and where level converter is needed we shall discuss later on. Okay, so, this is how the clustering can be done. Now, what is the impact of this clustered voltage scaling? So, normally you know, whenever you do static voltage scaling, say we have already discussed about it, static voltage scaling. That is SVS. There, if you consider different paths, a circuit may have large number of paths, and if you plot the path delays, this is the delay, path delay, and on the y axis it represents the number of gates on different paths. So, you can see in this part you have got gates which are on very close to the critical path, because this is the critical path delay. On the other hand, majority of the gates are on the very close to the typical delay of the circuit, and here is the critical path, and then some gates may be having lesser delay, may be having on the paths of lesser delay. Now, whenever you do static voltage scaling, you get a curve like this. How? That means the you have large number of paths and you have got different gates on different path delays, and accordingly you can assign voltages. So, you can say the different gates on different delay levels. So, this is these gates are in the medium range of delay path. So, this one, how it is modified whenever you go for multi-level voltage scaling. How this particular curve is modified? It modifies in this way. So, this corresponds to say single voltage scaling. As you do multi-level voltage scaling, it modifies in this way. Number of gates remaining same and critical path delay remaining same, a large number of gates which were having smaller delay on this side, now they are pushed to larger delay. However, they do not exceed the critical path delay. How they are pushed towards this larger delay? By assigning lower supply voltage. So, as you assign lower supply voltage, their delay will increase. That means, more number of paths will be having larger delay. So, that this is how it is modified whenever you do multi-level voltage scaling, and this corresponds to single voltage scaling. So, you can see how the path delay modifies as you go from single voltage level scaling to multi-level voltage scaling. Now, we shall focus on various issues in multiple VDD circuits. We have seen how you can assign multiple voltages at macro level, at standard cell level. It has got many challenges. That means, a circuit designer, if he wants to use multiple voltage domains or multi VDD circuits, they have to face a number of challenges and they have to overcome them. What are the different challenges? Let us consider. Number one is voltage scaling interfaces. As the signal passes from one voltage domain to another voltage domain, in those interfaces you will face some problem. What kind of problem we shall face? We shall discuss in detail. Then you will see that you will require level converters in the voltage scaling interfaces, and then level converters are to be suitably placed, and how and where they should be placed we shall be discussed. That is also a challenge. Then floor planning, routing and placement of not only different modules or different macros or standard cells, how they will be placed, how the routing will be done, how the clustering will be done, that will play a very important role. Then multiple supply voltages. Here the question will arise, how many supply voltages he will use, 2 or 3 or 4, that trade off has to be there is a trade off between delay and the reduction in power dissipation. That means, the gain performance in terms of reduction in supply in power dissipation versus the as in the overhead that being increased, overhead versus reduction in power dissipation, that trade off has to be solved. And then static timing analysis has to be solved, because you will see that static timing analysis will become complex, more complicated whenever you go for multi-level voltage scaling. Then power up and power down sequencing, whenever you turning on the power and turning off the power, that sequencing will become also difficult, and you have to solve that problem. Then clock distribution will be also it will be challenging in case of multi VDD circuits. So, let us consider one after the other. First, let us consider the voltage scaling interfaces. In this particular case, we have shown an inverter which is in the lower voltage domain with supply voltage VDDL, and the signal is going from VDDL to VDDH. So, what kind of problem you will face in such a situation? That means, you have got it need not be an inverter here, for the sake of simplicity inverter is shown. It is operating at a lower voltage VDDL, and signal from this inverter is going to another inverter which is operating at higher voltage domain VDD high. What kind of problem you can face in this particular case? The most serious problem that we will face is whenever this output is high, output of this first stage is high, it will produces a voltage VDD L. But what can happen, this VDD L may fall in the range of say it can be greater than VTN, but less than VDDH minus VTP of the this PMOS transistor. That means, if this happens, what will happen? That means, this voltage high level voltage is here, which is higher than the threshold voltage of this, and but this transistor also will remain on, because voltage is less than the VDDH minus VTP. So, what will happen? This will lead to what is known as short circuit current, as you know. So, there will be short circuit current, and this will lead to very high power dissipation. This is one problem we shall face. Second problem that we shall face is, whenever you are driving, even if this is not the situation, that means, if this condition is not satisfied, it may be higher than the VDDH minus VTP. Even then, the drive to this stage will decrease, because at high level this voltage is lesser than VDDH. So, delay of the next stage will increase, because of lesser drive that is coming from the previous stage. That means, whenever the signal is passing from low voltage domain to high voltage domain, then there may be drive problem that will lead to larger delay of the next stage, and also this may lead to larger power dissipation in the next stage because of short circuit power dissipation. So, this problem has to be overcome. So, how this problem can be solved? Quite often it is necessary to insert level converters or shifters that convert signals of one voltage level to another voltage level. So, you have to insert in between this low voltage domain and high voltage domain. Let us assume this is the low voltage domain and this is the high voltage domain. You have to put a level converter LC. So, level converter will raise the voltage level of this side to high level, it will receive input from lower voltage domain and produce output at higher voltage domain. That is the function of the level converter that is used in this case. So, this I have already explained. So, you require a level converter to avoid this static power dissipation on this circuit. How can you realize a level converter? So, this is the type of level converter you can use. That means, you will require a level converter which is given the symbol, there is a block, it is receiving input at low level, it is producing output at high level, and it is provided with VDDL, two different voltage supply voltages VDDH, and of course, there is a common ground. So, this is the symbol of a level converter. Inside a symbol is given here, which is essentially, that means it is changing the level, that it signifies that, and it can be realized by using a circuit like this. There are many ways it can be realized, but this is the most common form of level converter that is being used. So, in this case, as you can see, we have a two cross coupled PMOS transistors acting like a kind of flip flop. So, the base is the gate of this is connected to the collector of the other MOS transistor, I mean drain of the other transistor, and gate of this MOS transistor is connected to drain of the other transistor. So, these are cross coupled. Then you have got two NMOS transistors here, M1 and M2, which are receiving input from two inverters. So, low level input is given here, and you have got two inverters which are operating at low voltage domains, and they are applying input only to the NMOS transistor, not to the PMOS transistor. You note that this is very important. The inverter output is fed only to the NMOS transistor, and also the input to the next stage, the next inverter is also fed to the another inverter. That means, these two voltages, these two inputs are complementary in nature, because they are coming from the output of inverters. So, whenever this transistor turns on, this will force this point to go down to 0, turning on this, and as it turns on, this will this output will be forced to 1, and as it goes, it is become once, this transistor will turn off. There will be a kind of regenerative action. As a result, very quickly output will change to at this point, it will change to high level, and you will get the output. That means, when the input is low, you are getting output low, but since this particular inverter is having a supply voltage VDD(H), here the output will correspond to high level. Similarly, when this input is high, this output is low, and this output is high. This output is high means this transistor will turn on. This will make this particular MOS transistor to turn on, and this will make this high, and that will turn it off, and as it turn it off, then this voltage will be low, and you will get output low. So, that means, the input polarity at this point and at this point is identical, only difference is in their levels. So, if this voltage is 0 level, this you get 0 level here. If this voltage is high level, you get high level here. However, that means, here 0 corresponds to 0 volt, in this case 0 corresponds to 0 volt, but here high level corresponds to VDD L, and here high level corresponds to VDD H. So, that is the difference in the input and output. So, this kind of level converter can be used, can be realized. As you can see, this is little complicated, and obviously, you have to characterize over an extended voltage range to match different voltage domains of low and high side of voltage domains for accurate static timing analysis. So, as I mentioned earlier, static timing analysis will be a problem. That means, this particular level converter has to be characterized for different voltage pairs. For example, you may be having voltage domains, as I mentioned, it can the one can be 1.8 volt, another can be 1.5 volt, this is one pair, then it can be 1.8 volt and the 1.2 volt, or it can be 1.2 volt and 0.8 volt. So, this type of voltage pairs are there. So, this is your VDD H and this is your VDD L. So, for all these pairs, the level converters are to be characterized. By characterization, I mean what will be their worst case delay, what will be their power dissipation, and so on. So, these are to be characterized for different voltage pairs, because you may likely to use level converters at the interface of different voltage domains, circuits of different voltage domains. So, you may have several such voltage pairs. Okay. Now, coming to high to low level voltage level converters, what is the problem you can face whenever high to voltage level converters are used? So, without a level converter, the voltage swing of the signal reaching the low VDD domain is 0 to high VDD. So, in this case without level converter the voltage swing is more. This causes higher switching power dissipation and high leakage power dissipation due to GIDL effect. That means, in this case what you are doing an inverter which is operating at high voltage domain VDD H is driving another inverter which is operating at low voltage domain. So, in this case what happens here, there is a capacitor, this load capacitor has to be charged and discharged corresponding to this voltage domains. That means, the power dissipation will increase because the voltage is high. As you know, the voltage power dissipation is proportional to alpha L VDD square, in this case VDD H square than F. So, that means, the power dissipation will be unnecessarily high, and also since you are driving with a higher gate voltage, this will lead to higher power dissipation in this gate because of that GIDL effect, gate induced drain leakage effect. I have already discussed about it. So, this to overcome this problem, the another problem, the rise and fall time may be long, leading to increase in short circuit power dissipation. This is another thing here, since it is changing over a larger voltage, the rise and fall times may be little long, and that may lead to short circuit power dissipation of this stage. Because of all these reasons, it is necessary to insert a level converter even when signal is passing from high voltage domain to low voltage domain. So, the level converters which goes from high voltage domain to low voltage domain, this is the symbol, and you can realize in this manner. Here you can see it is essentially two inverter stages with a low level supply voltage. Supply voltage corresponds to low level voltage domain, and here you have got input coming from high voltage domain and output it is generated that will corresponds to low voltage domain. And in this particular case, circuit is quite simple. So, static timing analysis is simpler compared to the previous case in the where the circuit is more complicated. Okay. However, it introduces buffer delay and its impact on static timing analysis is small compared to the previous case. Okay. Now, let us come to the question of converter placement. We have discussed about different types of converters that you will require. Now, you have to place them. Where do you place them? As I mentioned, in a circuit you will be having different voltage domains. This will be one voltage domain, this can be another voltage domain. Where do you put the level converter? It is not that it will be placed in the middle. So, you have to either place them in the low voltage domain or in the high voltage domain. That means, if it is a low voltage domain and if it is a high voltage domain, either it has to be placed here or it has to be placed here. The level converter has to be placed where the placement is beneficial. So, this is a very important design criteria, design decision in the voltage scaling interface is the placement of inverter. Where do you place it? So, as the high to low level converters use low VDD voltage rail, it is appropriate to place them in the receiving or destination domain. We have seen that this particular level converters requires only low voltage domain supply VDD L. So, therefore, it is more logical. So, suppose this is VDD H domain and this is VDD L domain. So, it is more beneficial to place it in this domain because supply voltage rail is reaching the low voltage domain in any case. So, there will be no need to connect a low voltage power to this for this level converter. If you place it here, you will require, that means this corresponds to high voltage domain. So, you have to take the power, the low voltage domain power line to this side if you place the level converter here. That is the reason here, reason why it is advisable to place a level converter in the low voltage domain or destination domain. And the rise and fall time may be long, leading to increase in short circuit power dissipation. Okay, sorry. So, as the high voltage level converter use low VDD, so I have already discussed that. So, it is also recommended to place the low to high level converters in the receiving domain. So, that was the previous case. In this case also it has been found that it is beneficial to put them in the destination domain or receiving domain. So, at the low to high voltage converters require both low and high VDD supply rails. At least one of the supply rails needs to be routed from one domain to the another. So, we have seen a low to high level converter, voltage domain converter requires both the supplies VDDL and VDDH. So, wherever you place it, you have to take one of the power supply to the another domain, as it is shown in this case. So, here you can see this is a high voltage domain, this is a low voltage domain. So, level converter has been placed in the low voltage domain. So, there is no need to route the do the routing for low voltage domain power supply to for this level converter, because it is already available here. But you can see here it is going from low voltage domain to high voltage domain. So, a level converter is here which converts from low voltage domain to high voltage domain. So, in this particular level converter can be placed here or here, but it is beneficial to place in the low voltage domain, because this reduces some of the timing problems. But VDDL has to be taken from the low voltage domain to high voltage domain area. So, this will increase the routing area, and obviously your cost of routing will increase. So, this is the challenge of placement of level converter. Coming to floor planning, routing and placement. So, multiple power domains demands multiple power grid structure and a suitable power distribution among them. What is being done? You can see different rows. This is a row corresponds to high voltage domain without any shade, and this particular row corresponds to standard cell of low voltage domain. This is another row where you have got standard cells of low voltage domain. So, you have done the some kind of clustering, you have placed them in a particular row, row by row placement has been done for the convenience of connecting power rails. So, you can see on both sides you have got power rails VDDH, VDDL and VSS, that is the ground line, and then you are providing power from these power rails either from this side or from this side to high voltage domain and low voltage domain and so on. So, this is how the routing and placement is done, and you have to plan floor planning is also done, and whenever you are using multi-level voltage scaling. So, multiple power domains require multiple power grid structure and a suitable power distribution among them. As a consequence, it requires more careful floor planning, placement and routing, as I have discussed. It is necessary to separate low VDD and high VDD cells, because they will have different annual voltages. I hope this point is clear to you. So, whenever you are realizing transistors of different voltages, as you know, suppose this is a N well, this is a well, this is the structure, and if there is a MOS transistor here and this well is connected, say suppose this is your N type and this is P type, and this is N plus, this has to be connected to different voltages. So, this well has to be connected, this well has to be separated from voltage domain of another well, and a separation is necessary in whenever you are using multiple voltage domain, because this has to be connected to one voltage, this well has to be connected to another voltage and so on. So, this separation is necessary in multiple voltage domains. So, and typically a row by row separation is used, as it is shown in this particular diagram. So, you have to maintain some spacing between these rows. So, separations are required. So, this is about floor planning, routing and placement. Coming to multiple supply voltages, a number of studies have shown that use of multiple supply voltages results in reduction in the dynamic power from less than 10% to 50% with an average of 40%. That means, on the average you can have 40% reduction in supply voltage, I mean power dissipation. Question is, will how many supply voltages you will use, 2 or 3 or 4. So, it is possible to use more than 2, say 3 or 4 supply voltages. However, the benefit of using multiple VDD saturates quickly. That means, it becomes a point of diminishing return as you go from 2 VDD to 3 VDD or from 3 VDD to 4 VDD. So, and major gain is obtained whenever you use dual VDD. So, whenever you go from single VDD to dual VDD, there is significant reduction in power dissipation, but whenever you go from dual VDD to triple VDD, you do not get that much saving. So, it has been found that dual VDD versus single VDD system, the optimal lower that another point is what will be the supply voltage, and it has been found that the lower VDD has to be about 60 to 70% of the high VDD. And in this particular slide, different voltages are shown. This is the high VDD 1.5 with threshold voltage 0.3, and whenever you go for dual VDD, second supply voltage is 0.9 volt, and this is the thumb rule that is being used to choose the second VDD. Whenever you go for triple VDD, the other two voltages, that means the second voltage and third voltage is selected, which is 1.02 and 0.69, and the first one voltage is 1.5 volt. And whenever you use quad VDD, and this is the thumb rule used to choose different supply voltages. VDD 1 is 1.5 volt, VDD 2 is 1.154 volt, VDD 3 is 0.87 and VDD 4 is 0.66 volt. Okay. Coming to static timing analysis, as I mentioned, use of single supply voltage makes static timing analysis simpler, because it can be performed for single performance point based on characterized libraries. So, it will be operating at one voltage, and for different, I mean if you can consider the worst case process voltage and temperature variations and characterize corresponding to a single voltage. And as I mentioned, whenever you go for multiple voltages, then electronic design automation tools can optimize, I mean it becomes a more problematic decision for EDA tools, because in multiple voltage domains, libraries should be characterized for different voltage levels that are used in the design. EDA tool has to optimize individual blocks or subsystems and also multiple voltage domains. So, static timing analysis becomes significantly difficult whenever you go for multiple voltage circuits. Coming to the another issue, power up and power down sequencing. This is a very important system level issue, and to avoid power line glitches, it is not advisable to bring up all power supplies simultaneously. That means, suppose you have got 3 voltage domains 1.5, 1 and 0.8. You should not bring up all the supply voltages together, that may lead to power line glitches. So, to avoid those glitches, you have to plan a power sequence such that different domains can come up in a well defined order to satisfy correct operation, and you have to follow some sequence to achieve good performance. Particularly, reset can be initiated only after power domains are completely powered up. So, you will the power supply requires some time for stabilization. So, unless the power supply is stabilized, you should not reset a circuit. For example, and resetting the circuit is important to bring it to a initial known state, and that is why resetting has to be done only when the circuit is completely powered up. That is why the ramping up and ramping down is necessary to avoid overshoot and undershoot on the supply lines. Similarly, the last problem is clock distribution. As clock needs to be distributed across different voltage domains, the clocks have to go through level converters. So, just like signals are passing from one signal level to another one voltage domain to another voltage domain, clock may be also passing from one voltage domain to another voltage domain. So, you have to place level converters for the clock distribution circuit, and this requires that clock synthesis tool must understand the need for level converters and automatically insert them in appropriate places. To summarize, we have discussed multi-level voltage scaling in this lecture, and we have discussed two types of multi-level voltage scaling using macro level cells and standard level cells, and we have discussed various issues that we will encounter in multi-level voltage scaling. So, with this we have come to the end of today's lecture. In the next lecture, we shall discuss about dynamic voltage and frequency scaling, and also that continuous, that automated voltage and frequency scaling techniques. Thank you.